Hello and welcome to Chapter 2. Now we're going to continue to talk about the building blocks of Python, variables, constants, statements, expressions, etc. The first thing we have to talk about is constants. These are just things, we call them constants because they don't change. They are numbers, strings, etc. And we use them to sort of start calculations, or if something is greater than 40 hours, we're going to do something, and so 40 is the constant in that situation. So we have 123, we have 98.6, we have hello world, which is a string by enclosing it in quotes. We pass each of these things to the print function, and a side effect of the print function is that we see the output. So print 123, prints out 123, print 98.6, prints it out. So these are just really the syntax of constants, and without constants we can't write really much of anything. The other sort of foundational notion of any programming language are the reserved words. And like I said before, reserved words are these special words where Python is listening for them, and there are very special meanings. So when Python sees if, it's not just any other word, it means how Python implements conditional execution. Variables are the third building block, and that is a way that you can ask Python to allocate a piece of memory and then give it a name. And you can put stuff in that. Sometimes you just put one value. Later we'll see when we do collections in chapters 8 and 9, we will see that more than one value can be put into a variable. And the variable, how we control the variable is through the assignment statement. And as I said before, it's important to think of the assignment statement as having an arrow to it. So this is not saying x for all time is the same as 12.2. What it's saying is take 12.2, find a place, find some memory in your computer there, Mr. Python, give it a label x, we get to choose the x. That's the variable part. We chose it, right? And then stick 12 in it. And then the same is true for 14. Go find another spot, name it y, and then put a 14 in there. So think of this as an arrow every time you see that equality, the assignment in an assignment statement. Now, these variables hold one value. So now if we have these three statements, these two, and then the third one executes, it says put 100 into x, but that wipes out the old value of 12.2, and it rewrites it with 100. And so we can change the variables. That's another reason that we call them variable. There are some names, now some rules for making variable names. You can start with a letter or an underscore. We tend not to, as normal programmers, use underscore. We tend to reserve those for variables that we use to communicate with Python itself. So when we're making up a variable, we tend not to use underscores as the first character. You can have letters and numbers and underscores after the first character, and they're case sensitive, but it's really a bad idea to use case as the only differentiator. So in this case, spam, eggs, spam23, and underscore speed are all totally legit. We would probably not use this one unless we were actually doing it because Python told us to use that variable. 23 spam starts with a number, pound sign starts, and dot is not a legitimate variable character. And spam, capital spam, and all cap spam are different, but this is not something that you want to sort of depend on too much. So that's just the rule names. We tend to start them with a letter and then use letters, numbers, and underscores. Underscores other than the first character are generally pretty common, and you'll see those used a lot. Now, when we're choosing variable names, one of the things about variables is we get to choose the name. We get to choose the name x, choose the name y. And so sometimes we like them short, but sometimes we want them descriptive. And the notion of making variables descriptive is often confusing to beginning students. Sometimes it's really helpful to, if you're going to have a line of text and you name the variable line, that's great because the next person reading your program says, oh, that must be the line of text. Whereas it also can become misleading that the name of a variable somehow has meaning. And so sometimes we'll have even singular variables and plural variables like friend and friends. And you're like, is plural? Does Python know about singular and plural? And the answer is no. So sometimes we pick variables that make no sense. Sometimes we pick variables that make a lot of sense. This is just something that you as a beginning programmer are going to have to understand, that we can pick anything we want. And so you'll see, I'll try to call attention to this in the first few lectures as we go through. So here's a bit of code with an assignment statement, two assignment statements, a multiplication, and a print statement. And you can say, what is this doing? Now, Python is perfectly happy with this code because it assigns it in there. You have said, please go give me this as a label. And then we assign two variables, and then we're carefully pulling these two variables back out, multiplying them together and sticking them into yet another variable, and then printing that variable out. That seems like, you know, we can figure out what it is. You just have to look really carefully. And a single character mistake, and Python is going to be, you know, pretty unhappy. Okay? So that's one way to write this program. It's hard though, because any of those characters are long variables and they're random stuff. It's not very friendly to anyone who might read your program. Now this looks a little friendlier. It's the same program because Python just wants a correspondence. You picked A, you picked B, and you picked C, and it's really much easier for us to see what's going on. And so this is, in a way, going from here to here is much friendlier, but we can be even friendlier if we pick mnemonic variable names. So this is not mnemonic, this is short and convenient, this is long and inconvenient. Python is happy with any of these. Here, on the other hand, is another version of the exact same program. And now you think to yourself, oh yeah, now I get it. 35 is the number of hours, $12.50 is the rate, and then we're going to multiply the hours and the rate and come up with the pay, and we're putting out the pay. Now whoever wrote this program is helping us greatly understand what's going on. And that's good. Choosing variable names. Python, again, all three of these are the same to Python. Choosing variable names in a way that help your reader understand what's going on is a great thing. The problem is, the danger is, if you read this and you think that somehow Python understands payroll, that if you name a variable hours, that Python knows what hours means. The answer is Python really doesn't care what you name the variable as long as what you name it, you use it, right? And so you got to be careful. And so you'll see, I will, when I write my code in these first few weeks, first few lectures, I will sometimes write it with gibberish. I'll sometimes write it with extremely short but meaningless variable names. And sometimes I'll use meaningful variable names. And I'll call your attention to it, and it will get you. You'll start, when you look at this third kind, it has meaningful variables or mnemonic variable names. You'll just instinctively want to give Python more intelligence than it sort of deserves. I guess that's probably the best way to say that. So we've talked about constants, we've talked about reserved words, we talked about variables. And so here we have a sentence, like we've already done some of these things, where we set x equals 2, we retrieve the old value of x and add 2 to it, so that becomes 4, and then we print 4 out. Print is a function that's built in, and we pass in whatever we want to print out. So this parentheses is part of a function call. Okay, so an assignment statement, you have to really get your head around the notion that it has this arrow nature and that it evaluates this entire right-hand side before we change the left-hand side. And so you can think of this sort of as at time step 1 it does this, and then at time step 2 it does the copy. And that's how you can have something like x on both sides of an assignment statement. And so if, for example, we have x and x has 0.6 in it, x has 0.6 in it, what happens is that it sort of ignores this part right here and evaluates the expression. So it pulls the 0.6, everywhere x appears, it pulls 0.6 out, then it starts running these calculations, and then it has the new value. After all the calculations are done, then and only then is it going to put that back into x. And so it sort of takes that and puts it back into x and then wipes out the old value. At this point, this has all been taken care of and it's been reduced down to this 0.93, and so that is what's put in as the new value. So up next we'll talk a little bit more about making more complex. We're going to talk about expressions. Expressions are a little more complex calculations that we can sort of do on the right-hand side of an assignment statement. So one of the things about expressions is operators. And the operators in computer programming are often very much the same as the mathematical operators, but we don't have all the fancy characters that we have in mathematics, and so we have to choose what's on the keyboard. And then we really go back to the 1960s and 1970s, And we used what was on the keyboard in the 1960s and the 1970s to make these operators. So plus is addition, minus is subtraction. We don't have a times sign or a dot in the middle, so we use the asterisk as multiplication. Division, we can't put two things over top of each other, so we use slash for division. Raising to the power, because it didn't have little characters back then, is star star, which is raising to the power. And then remainder. Remainder is when you do integer division, it's also called the modulo operator, it's the remainder, not the quotient. Now I've got a picture of that coming up. So here's a whole series of little examples of this. Right, so we've already seen, the plus, x equals x plus 1. Keep remembering that these assignments are arrows, basically. Arrow, arrow, they have a direction. Multiplication, 440 times 12. Dividing this by, that's division, over 1,000, 5.28. Here we're going to put 23 into JJ, and then we're going to do modulo. So that says, take 23, divide it by 5, and give me back the remainder and put it in KK. So this is the expression that evaluates like this. Take 23, divide 5 into 23, 4, remainder 3. The 3 is what comes back up here. Okay, and so that is the remainder. It's also called modulo operator. It turns out that for things like picking a random number and then taking the modulo of 52 as a way to pick a card randomly. So this modulo operator is actually, especially in games and other things, super useful. So that's the various operators. It's important to know which of these operators goes first. That's called operator precedence. Now normally we put parentheses in, like, so if I put the parentheses in here, I'd say this goes first, parenthesis, then this goes first. Oh, actually not that one. Oops, got that one wrong. This happens first, this happens, then this happens. Okay, and so, but it's important for us to be able to know, if there were no parentheses, the order in which these things will happen. So the way things work in terms of operator precedence is parentheses are the most important thing, followed by raising to the power, all else being equal. Multiplication and division are all both equal, and then addition, and then within it's adding left to right. So let's see an example of how this works. And so if we take 1 plus 2 to raise to the 3 power divided by 4 times 5. And we print out what comes out of this. So the way I did this when I was taking exams back many, many years ago when I was first in computer science is I'd write it all down and I'd look for the highest precedence thing. Now parentheses would make this easy, but exponentiation is the first one. So that means we're going to take this, and that's going to be 8. 2 to the 3rd power, 2 times 2 times 2, 2 cubed is 8. Then what I would do is I rewrite the whole thing with the 8 there. And now I look across and I'm looking for multiplications because the power's been done. The multiplication is what I'm looking for next. And then there is both multiplication and division. They're equal. They're at the same level. And so what happens is they're done left to right. 8 divided by 4 happens before 4 times 5. And so the fact that it's not 4 times 5 but instead 8 times 4 is because of the left to right rule. So then this gets rewritten to be 2, 1 plus 2 times 5, and this one, multiplication, is the top one, so that does this next. 2 times 5 becomes 10, I rewrite it again, and then 1 plus 10, addition is the lowest thing, and that's how we end up with 11. And so that's how I would do these problems if I ever saw the problem on an exam. And it's a fun problem to put on exams because there is one and only one answer, and every programming class has usually at least one slide about this stuff. So like I said, the rules go top to bottom, parentheses, power, multiplication, addition, and then left to right within it. So we talked about variables and computing values to put inside variables, but the one thing you've kind of also, maybe you noticed it as we go by, is we have different kinds of data. We call it type. Is this of type integer? Is this of type floating point number? Is it of type string? What is going on here? And Python is pretty smart about various kinds of types of data. And so, we're adding 1 plus 4 here, and Python knows as it looks at this that that's an integer and that's an integer, and we'll add it together and make it an integer. So that thing is an integer. We can also use this plus to concatenate two strings. This is hello blank plus there. And plus looks here, says, oh, that's a string and that's a string. So I know what to do with strings. I will concatenate those two things together so it becomes another string that gets assigned into EE, and it's hello space there. The plus doesn't add the space. I added the space by putting it right there. And so these operators are kind of smart in that they kind of know what they're dealing with, and sometimes they will do one thing or another depending on the kinds of values, variables, or constants that they're working with. And so sometimes type can get us in trouble. So here we have EEE, which is hello there because we've concatenated these two strings together. And now we're adding 1. And the problem now is that it looks on one side and says that's a string and that's a number and says I don't know how to do that. This is another one of those annoying errors that you think that somehow Python doesn't like you, but it just is confused. If you look at these things, traceback always means I quit. It means I stopped, I ran, I'm quitting now because I don't want to go any farther because I've become confused. So your program stops running and you say, here's where I stopped running. Because we're typing interactively, it's always line 1 here. Type it, but if you read carefully and you don't get too stuck on too much stuff, line 1 that tells us something. In module type error, can't convert int object to str implicitly. So that's an integer right there, and that's a string, and that's what it's complaining about, that little bit right there. If Python is so grumpy about types, then we should be able to ask it about types. So there turns out that there is, inside Python, a built-in function called type, T-Y-P-E. So we can pass into type. So the syntax is calling a built-in function named type, parenthesis is the parameter that we're passing to it. We're saying, hey, hello, tell me something about the type of the variable EEEE. And so this is a function, the parentheses are part of the function call, and it says, oh, that would be of class string. And then we can pass in a constant and says, hey, what about hello? The string hello, it's like, oh, that's a string too. What about a 1? Well, that's an integer. And so we are asking Python through the type function what the type of either a variable or a constant is. And there are even several types of numbers, and we'll even see Booleans and others later. Like 1 with no decimal, that's an integer number. 98.6 with a decimal, that's a floating point number. And so, constants can be both integer and floating point. And I'm just asking over and over and over again, what is the type of what's in XXX, what's the type of what's in temp, and what's the type of the constant 1. And what's the type of 1.0. You can also use a set of built-in functions like float and int to convert from one to another. And so this basically says, I want to convert, let's go back. I want to convert 99 to a floating point number. So this is a function and it's participating in this plus, but before it can finish the plus, it turns this into a 99.0. The difference between 99 as an integer and 99.0 is that it's a floating point number. And that actually turns this computation, as it looks to the left and looks to the right, says, oh, I've got a floating point number on one side and an integer on the other side, and so I'm going to make my calculation overall be a floating point calculation. I can also pass into the float function. I can say, take this variable I, which has a 42, also an integer, and then give me back a floating point. So that'll be 42.0. Pass that into F, we print it out, and it is indeed 42.0, and it's a float. And so it knows the type and value in any variable. This is an integer, a value 42. This is a float, a value 42.0. Integer division in Python 2 was kind of weird, and it was actually one of the big things that they changed between Python 2 and Python 3. This is a Python 3 course, so we're not worried about that too much. What's nice about integer division in Python 3 is it always produces a floating point result. And that means that Python 3's division is more predictable and it works more like a calculator. So in this case, I mean, you can go back and look at my Python 2 lectures and see how crazy it was in Python 2. 10 divided by 2 is 5.0. And the weird thing here is these are both integers, but the division forces the result of the calculation to be a floating point number. And this, 10 over 2 could be 5. But 9 over 2 is 4.5, and so that is accurate. In old Python 2, that would give us back 4, which is completely unpredictable and weird. The same with 99 over 100. As you would expect, if this were a calculator, you get 0.99. Actually, what you get in Python 2 is 0, because it would round it down. It doesn't round at all, it truncates it. So 99 over 100 is 0.99, and then it truncates it to 0. That's Python 2. We're not talking about Python 2. There's a good reason we're not talking about Python 2. Welcome to Python 3. Of course, if there are a floating point on either side, the result is still a floating point, and the result is still a floating point. So integer division produces a floating result in Python 3.0, not in Python 2.0. That is an improvement in Python 3.0. And that's why we're recording these lectures. I have a whole great set of lectures about Python 2, and now I'm going to have a great set of lectures about Python 3. Welcome to Python 3. Okay, so we've been talking about converting from integer to floating point, but you can also convert from string to integer or string to floating point. And so here we start out with a little string value. Now it only works for strings that are made of digits. So quote 1, 2, 3 quote is not an integer. It is a 3-character string that has 1, 2, 3 as the characters in that string, which is very different than 123. We say, what is the type of this? It's a string. We say, let's add 1 to it. And it says can't convert into string, so that blows up, right? Because this is a string. It looks to both sides. String plus an integer, not good, okay? But we can convert this. We can call the int function, which is like the float function, and pass a string in. So it says, hey, take this and turn it into an integer. So take the input of sval, which is the string 1, 2, 3, and give me back an integer representation of that, which is going to be 123. So we say, what kind of thing do we get back? Well, we got back an integer. We can now add 1 to it and get 124. And so you have to manage the type of things, and you can convert from one type to another. Now, int is not magic. If you send something into it, a string that doesn't consist of digits, then you're going to end up with another error. Invalid literal for integer with base 10, blah, 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 blah. So it's really complaining. It says, I want these to be numbers here, and you just gave me letters, so that's going to cause this to fail. Another thing that we're going to do with variables is, just like the print function takes something, a list of things, in this case, a string, comma, a variable, and then prints some output in the program, the opposite of that is input. Actually, input generally happens before output. Input is a built-in function, and we pass to it a prompt, a string of text that's going to be printed out for the user, and then it stops and waits. So it says, who are you? And then right here it just sits, waiting for us to type something. So we type blah, 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 and then hit the enter key. Right? We hit the enter key, and then this text ends up in this variable. So this is an assignment statement that Chuck is the result of the input call, gets copied into the NAM variable. So let's do that again. It's evaluating an assignment statement. Remember, it's kind of this way, or you can think of it as just do this right side first. It writes this out, writes that out, then it waits, wait, until we hit the enter, and takes this Chuck, and that becomes the result of this input, which is then assigned into NAM. Now then we go sequentially to the next line. It prints out welcome, comma, contents of the variable NAM. Now this one, this comma here, actually does put the space in here automatically. So it says welcome space Chuck. So it pulls there's no space in Chuck, just the CHUCK. And so print can take more than one thing separated by commas. As a matter of fact, print can have, a whole bunch. Oops, come back. Print can have comma, 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 parentheses, as many as you like. Everything you've seen up to now is kind of one thing in the print, but that doesn't mean that print only can do one thing. So I've talked about variables, we talked about constants, we've talked about input, we've talked about output, and now it is time to write our first meaningful program. And so this program has to do with those of you who have traveled internationally. If you traveled to the United States and you traveled outside the United States, you notice that there is an elevator convention that is different inside the United States. In the United States, the walk in the ground floor in the elevator, that's 1. And if you walk in the ground floor in Europe or many other places in the world, in the elevator is 0. So we have written a small app that we're going to put on the App Store and get wealthy with called Elevator Floor Conversion App. And it's going to ask us, we're in Europe and we're lost, and you say, well, what floor would this be if I was in the United States of America? And so we have to read the floor that we are at in Europe, and then we're going to convert it to a US floor, and then we're going to print it out. This is very silly, but it is a pure essential program that has input, does some kind of task on that input, and then produces some output, which is useful for some value of useful. Okay? So let's take a look at how we combine everything that we've learned in this lecture, input, processing, and output. It's a 3-line program, but it's sort of the beginning of something that programs do. Okay, you're going to do lots of programs that do this. So here we go. Program starts. We do the input, side effect. It prints out this and then waits. We type in 0. That comes back here. And the 0, which is a string. Input gives you back a string. It doesn't give you back a number. It was a little different in Python 2, but in Python 3, input gives you a string. So quote 0 quote, which is what we typed here. We didn't type the quotes. It's a string. Gets stored in the imp variable. Then we move to the next statement. And on this right-hand side, we convert that string variable to an integer, so that becomes the integer 0. We add 1 to it, and then that becomes 1, and then we assign that into USF. I've named this variable United States floor, right? So imp is the input, and USF, that's mnemonic. It doesn't know anything about elevators. It's just I picked a variable that was quite friendly. And so at this point, USF has the United States floor that's equivalent to the European floor, and then I just fall down and I do a print statement. Print out US floor, comma, that's this space right here, and then whatever the contents of the US floor variable is. And you could see that I could write this on 4, and it would say 3. I could write this and say 7, and it would say 6. This is an amazing program. It converts floors in a European numbering scheme. Wait, actually no, I got that wrong. Hang on. Let me clear this. I wasn't thinking clearly. I could type in 4 and it would give me back 5. I could type in 6 and it would give me back 7. See, I'm confused. Haven't been in Europe in a couple of months, and so I forgot all about the floors. But that's the idea. Now, this is a super simple program. Not super useful, but you get the idea that we're going to pull some data in. We're going to do some intelligent thing. Soon this will be hundreds of lines of code instead of 1 line of code. And then we go and present the results to our user. Now, another element of most any programming language is what's called a comment. A comment is a way for you to put in a program file some text that's to be ignored by Python or C or whatever language we happen to be using. In Python, comments start with a pound sign. So what you could do is put a pound sign anywhere in a line, and then after the pound sign, Python ignores everything after that pound sign. It can be the first character. So here's our recurring concept that we talk a lot about. We're not going to cover this. Remember what this does. This is counting how many letters. There's 16 thes, and there's in that file there was 6 2s or whatever it was. This is that code. We'll get back to this code. But what we've done here is I've added some comments that are really for human consumption. So this first paragraph is get the name of the file and open it. The second paragraph is count the word frequency. You know, maybe I should have said histogram here. Count the word frequency and assemble a histogram. And then here I'm putting this pound sign in, find the most common word, and then I'm all done. I print the stuff out, right? And so all I'm saying is comments are for people to read. Your next programmer or the person who's going to change your program after you're done with it. And they're nice, and you don't have to use any particularly weird syntax or variable naming conventions. You put a pound sign in, and you can write anything you want from that point forward. Okay, so we've talked a little bit about variables and types and mnemonics and how we would choose variable names and how expressions work and the various operators, converting between different types, printing, input, output, and comments. So that just kind of gets us sentences. And coming up next, we'll talk about conditional execution, where we're really starting to move up to paragraphs. So see you in a bit. Hello and welcome to Chapter 3, Conditional Execution. In conditional execution, we meet the if statement. The if statement is where Python can go one way or another way, and it's the beginning of sort of our way of making Python make decisions for us. Sequential code, we just do some things. Sometimes that's useful, but now we can have our code check something and then make a decision based on that thing. So the conditional steps in Python are pretty straightforward. The keyword that we're going to use is the if statement. And so if is a reserved word. And the if statement has as part of it a question that it asks. And this is asking if x is less than 10. and the colon is the end of the if statement, and then we begin an indented block of text. And the way this works in this particular thing is this line is the conditional line. If the question is true, the line executes, and if the question is false, the line is skipped. And you can think of it the way this is, right? X is 5, ask a question, is it 10 or not? These questions do not harm the value of X. If it is, then we run this code, and then we sort of rejoin here, and then we test this next if, and if that's true, we do this code, and then we do there. But in this case, it's going to be false because X is not less than 20, and so it just continues down here. So if we look at how this works, it runs this line, then it sees this question, it skips that line. So this line does not run, and so smaller prints out and fini prints out. Okay, and so that's the basic idea of an if statement. And the indentation, when we are done with an if statement, we de-indent back, and there's this little block. This is one sort of if statement, and this is another if statement. And these are the two conditional lines that either run or they don't run, depending on the question, the answer to that question. So we have a number of different comparison operators that we can use to ask these true-false questions that say, is this true? So again, we're kind of limited to the keys that were on computer keyboards in 1940s and 1950s, less than or equal to. So we didn't have fancy math characters, so we just concatenated less than and equal to be less than or equal to. This double equals is the asking, is this equal to? And so that's a little tricky. The equal sign is that assignment operator. If I was building a language today from scratch, I would probably make assignment be arrow and the equals question to have an equals. Or I might say, somewhere I would say question equals. But I'm not building this language, so it's not up to me. So this is the question. Double equals is asking the question is equal to. Greater than or equal, greater than, and not equal. So this is the exclamation point is sort of like not equal. So that's sort of not equal. So that's how we do not equal. So if we take a look at some of these in some examples, all of these are going to be true because of the way X is set. If X is equal to 5, that's the question version. That's true or false. It'll execute that. If X is greater than 4, it's going to execute that. If X is greater than or equal to 5, it's going to execute that. Here's kind of a shorthand where if there's only one line in this block, you can kind of pull it up right on the same line after the equals. If X is less than 6, which it is, true, execute that. Then if X is less than or equal to 5, do that. And if X is not equal to 6, do that. Now, like I said, all these questions have been carefully constructed so that they're true, just to kind of show you the syntax of those comparison operators. Now, you don't just have to have a single line of text in the indented block, and this will be something you're going to get used to. So if we indent more than one line, then the conditional code is actually these 3 lines. So the idea is you have an if statement, you come in, you do an indent, and as long as you stay indented, you stay in that if block. If it's false, it just skips all of those. So the way this is going to execute, X is 5, we print before 5, is X equal 5, that's the question mark, and that's true. So it's going to run all these, and then come back, and then continue on in the de-indent, so all this stuff is running, right? And then it says X equals 6, well that was false, so that skips all of them. So none of these lines of code run, so these actually don't run, and it says afterwards 6, so that's a mistake. Those don't run right there, okay, because X is not equal 6. Okay, so indentation is an essential part of Python. We use indentation in lots of programming languages, often to kind of demarcate blocks, to show where blocks start and stop. But in Python, it's syntactically correct. You can make an error if your indentation is wrong. After an if, you must indent. And you maintain the indent as long as you want to be in that same if block. And then when you're done with the if block, you reduce the indent. In this rule of indenting, comment lines and blank lines are completely ignored. So we're going to tend to like put 4 spaces. 4 spaces ends up being the normal thing that we do, and you'll see all the code that I write has 4 spaces for each indent. If I go in twice, I use 8 spaces. And we have this instinct of wanting to hit the tab key to move in 4 spaces. Now the problem is that it might look the same on your screen. A tab and 4 spaces might line up the same place depending on how tabs are set. But Python can get confused by that. So we tend to avoid using actual tabs in files. And so most programming text editors, like if you're using Notepad or Text Wrangler, there's a place to set the tabs to say don't put tabs in this document, but every time you hit a tab, move over 4 spaces. And so you hit a tab, but it's like space, 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 space. Now the nice thing about Atom, and this is the text editor we tend to recommend in this class, because it works on Windows, Linux, and Mac, but also because it automatically sets this up. As soon as you save your file with a .py extension, you can sort of hit the tab key with impunity, and everything works perfectly. But the key thing here is that Python insists that you get this right, and if you don't get this right, you're going to get indentation errors, and they're just another syntax error. So if you're using something like Text Wrangler or Notepad, hunt around in the preferences and you'll find something about expanding tabs, or maybe how many spaces each tab stop is supposed to be. And so you check these, and what this really is doing is telling your text editor never put an actual tab in the document, but somehow simulate tab stops using spaces. And so here is a bit of code. It's got a nested block, but it gives you this sense that you have to be very explicit when you're reading Python code of whether the indent is the same between 2 lines, the same, increased or decreased. And so every time you increase it, you mean something, and every time you decrease it, you mean something, and literally if it stays the same, you mean something as well. And so if we take a look at this, here we have a line, and the next line has the same indent. This is an if with a colon at the end, so we have to increase the indent, and now we're maintaining it, okay? So these 2 lines are part of that if, but now we have de-indented. So whether you choose to de-indent this word or whatever, where you do this de-indent affects the scope of how far this if statement lasts, right? It lasts up to, but not including, the line that's de-indented to the same level as the if. Okay, so this is a de-indent. Now we have a blank line, which doesn't matter, and we maintain it. Now we have a for, which we'll learn about in the next chapter, which is a looping structure. Let's do a for runs this 5 times. It has a colon, and it also expects an indented block. Now we have what's called a nested block, where we have an if and a colon, and we go in some more. So this is like 2 indents, right? So these are 1 indent, and these are 2 indents. And so this is a block within a block. And then we de-indent, so that means this print is not part of the if statement, but is still part of the for statement. And then we de-indent again, and then that means this print is sort of on the same level as that for statement. So if you start thinking about this, you want to be able to start thinking that these blocks are the start of the block with the colon line up to but not including this line that's been de-indented. So the for goes this far, right? The for goes up to but not including the line that's de-indented. The if goes up to but not including the line that's de-indented. So as you do this, you'll sort of mentally start drawing these blocks, and pretty soon you will start constructing them as blocks. And it takes a while, but doesn't take forever. But in Python, unlike other languages, you have this is very important, and it matters, and you can have syntax errors if you get it wrong, because you're really communicating the shape and structure of your code using these indents and de-indents. We already saw a nested indent. This is a nested if, so you can put an if within an if, and you can go as far deep as you want to go, like Russian dolls. And so here we have x equals 42. If it's 1, we indent 1, and then with this next thing we do, these are at the same level of indent, but now we see an if, and it has to indent further. So this is like 2 in, 8 spaces, and then we de-indent back. Actually, we de-indent back 2. And so if you watch this and you take a look at how this works, it runs to here. Oops, back up. Comes in here. The answer is yes, x is greater than 1. Prints this. Is x less than 100? Well, it's 42, so the answer is yes. So it runs this, and then it kind of continues back to there. And you can also think of drawing boxes around this. This is one if box, and then within that if box there is another if box. And again, it's the indent the indented block up to but not including where the de-indent happens. And this here is like two backwards de-indents. So it ends two blocks. So two blocks are ended by where we place this. We could move this in or we could move this out. We could have it all the way into here, we could have it to here or here. And where we put that line depends on how the ends of these blocks are going to work out. So one form of that's a one branch if that we just saw, but then you can also have what's called a two branch if. And the basic idea of a two branch if is that you're going to come in, you're going to ask a question, and you're going to go one direction if it's yes and another direction if it's no. We call this an if then else. It's kind of like a fork in the road. And the way to think about it is depending on the output of this question, we're going to pick one or two of these, but if we pick one, the other one's never going to happen. So it's like an either or. We're either going to go one way or we're going to go the other way, but there is no path where we somehow go boot through both of them. That doesn't happen. And the syntax that we use for this is what we call the if then else. And so the first part is a normal if with an indent, and then we de-indent, and then this is another reserved word, else, with a colon, and then we re-indent. And so this is really end up being part of a whole block here, and the else is the part, this is the part that runs if it's false, and this is the part that runs if it's true. The first branch of the if, the first indented block is what runs if it's true, and the second indented block is the one that runs if it's false. And so here we go, just if x is greater than 2, in this case it's yes, we're going to print bigger, and then we're going to be all done. And so we do one, and so this one did run, and this one did not run. So basically with an if then else, one of the two branches is going to run, but there's no case in which both branches run. And again, you sort of draw these blocks around these things mentally, and in this one you sort of take from the if, not the else is really part of the block, up to but not including that print, which is back indented, de-indented back to the same level as the if statement. Okay? This Python is actually one of the more elegant languages, even though after a while this indenting and when you get too far in it gets a little bit complex, but this is a good way to visualize this with these indents. Coming up next, we're going to talk about some more complex conditional structures. So welcome back. Let's talk a little bit more about some more complex conditional statements that sort of build on this concept of if and if then else. The first thing we're going to look at is the multi-way branch. And so the idea is it's kind of like the if then else where you're going to pick one of two, but now we can pick one of three or one of four or one of five. And it introduces a new concept called the LF. The LF is another reserved word inside Python. And the way it works is it's probably best to look at this here where it checks the first one, and if it's a true, then it runs that and then it's done. It doesn't check them all. It's not like it sees that there are two logical conditions. It actually checks them, the first one, and how you order these matters, as we'll see in a bit. And so if the first one is true, it runs. If the first one is false and the second one is true, it runs this one and it's done. And if the neither of them are true, it falls through and there's an else clause that is otherwise, and it runs that. So basically it's either going to run one and then skip the other two, or it is going to, skip one, skip two, and then run this one. But it only runs in this case one of them. But the important thing is it checks these questions in order. And it doesn't check the second question until it finds that the first, it doesn't check the second question until it knows the first question is false. So if the first question is true, you're done. You're done, and you're done with this. You're done with the whole block at that point. So only one of these three is going to execute in that block. So here's sort of some examples of this. If we, for example, have x equals 0, it's going to come down here. X is less than true. That's true. So it runs this code, and then it skips down to that. And so it's like this, runs that code, and then skips to the end. Okay. On the other hand, if it's 5, then this is false, and it skips that, and it checks this. This is true. It runs this code, and then it's done, skips to the end. It goes like false, true, run, end. And then if x is like 20, for example, it runs, false, false, run the else clause, and you're done. So skip, else, run that code, and you're done. So in this case, we ran that, and we didn't run that, and we didn't run that. Again, one of them's going to run. They're checked in order. These questions are checked in order, not out of order. It doesn't look ahead. It just checks in the order that you wrote it. You're the one that wrote that order. And so there's a couple of variations on this multi-way. You can have no else. You can have no else, as in this case. And this just means that it might not run any of them. In this case, x is 5, so it's not less than 2, but then it runs this one. But if x was like 50, for example, if x was 50, then this would be false, then it would skip, and this would still be false, and it would skip, and neither of these two would run. So if you don't have an else, you're not guaranteed that one of them is going to run, because else is like the catch-all. If the other ones are all false, then the else is the one that runs. Similarly, you can have many elifs. But this is where it's really important for you to make sure you know what order they're being taken in. So that I've got, this, if this is true, it runs, it goes all the way to the bottom. If, this was, if it's false, 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 true, it runs this one and it's done. If, on the other hand, it looks at it as false, oops, go back. If it runs false, 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 they're all false, then it runs the else, right? This one has an else, this one didn't have an else. They don't have to have them. The key is you can have more than one of these elifs, okay? So I got a couple little things. I'll let you pause right now and look at, the question is, are there, looking at the 3 lines or 4 lines of code, x equals something. Are there lines of code that will never execute regardless of the value for x? And I'll let you pause and think about it, and then I'll explain it to you. Okay, hopefully you paused and thought about it as long as you like, but so let me now explain it to you. So we come in here, and if x is less than or equal to 2, it's going to run this first thing, and if x is greater than or equal to 2, it's going to run this, and if neither of those are true, then it's going to run this. Well, the weird thing is, all numbers are either less than 2 or greater than or equal to 2. I carefully constructed this to the point where it would never run this line of code. It is either going to run this one or run that one, but it's not going to ever run this one. So that was kind of like a weird dysfunctional one that I constructed. This other one is a little different. If x is less than 2, we do this. If x is less than 20, we do that. If x is less than 10, we do that. And if none of those are true, we do that. Well, the problem here is between these two lines. The problem is if something's less than 10, like 6 for example, it's also less than 20. So even though there might be values for which this is true, those also are going to have this true. So for something like 6, it's going to run here, and it's not even going to look at this. That's the point. It doesn't even look at this. And so that's, I mean, I could have made this more sensible if I'd have moved this little block of code up to there. So this is where the order in which you choose your questions, the way you put these elifs together matters, because it doesn't look at all of them. It only looks as long as it can. As long as it sees falses, then it keeps on going to the next one. But as soon as it doesn't see a false, it doesn't continue. So the last conditional structure we'll talk about is the try and except structure. And if you know any other languages like C++ or Java or JavaScript, you're like, whoa, that's kind of an advanced concept. But it turns out in Python, because of Python's propensity to throw tracebacks in situations where you kind of would like to recover, it turns out you kind of have to use it a little more and a little earlier in your programming skill. So the problem is what if there is a line of code and you absolutely know it's going to make a traceback, it's going to blow up, but you don't want to blow up. I mean, I don't want to have code blow up. If you're using my autograder and you see a traceback in my autograder, that's kind of like, I consider that a failure. I could put an error like, hey, you entered blank data, or you didn't enter a number, but a traceback, that just seems like I'm too lazy as a programmer. So we as programmers are supposed to anticipate parts of our code that are going to blow up potentially based on perhaps the user's input, and then do something about it. And that's what the try and except are for. It's you take this little dangerous piece of code that might break and might blow up, and you surround it with a try and says this might blow up, and if it fails, run this code down here. Okay, so that's the try, and if you get an exception, the except is kind of like if you get an exception. And the problem is if you are running code, here's a little bit of code, we put hello Bob in and we convert it to an integer, and we know from past experience that this blows up, right? You can't take hello Bob and convert it to an integer, it's just going to blow up. The problem is, and you know, here we are, it says, oh, you blew up on line 2, that's great, and I'm not very happy with hello Bob, and whatever. But the important thing is your program stops. These other lines, they don't, oops, these other lines, they don't exist, right? It doesn't go any further. Remember, the traceback is Python is really confused and I don't know what to do next. So Python is just going to be conservative and stop. So Python stops and your program stops. No matter how much error checking you put down here, it doesn't matter because it's gone. It's all gone. And like I said, we take this kind of personally because the code that you write is like you being put into the computer, giving it instructions. And if the code blows up, well, that sort of wipes you out. You're not in the game anymore. You're not able to do anything. So we want to be able to, especially in these situations where we can anticipate that an error that might happen in the normal course of your program's execution might be something that you want to compensate for. And that's what the try and except does. So here's a bit of code for the try and except. And we just have 2 little bits of straight line code. And so we put a string in here that's hello Bob, and then we're going to convert it to an integer. This is the dangerous code. This code in this case with hello Bob is going to do a traceback. And so we say try, and then we indent the dangerous code, and then we add this little except bit. If it works, the except is ignored. If this blows up, it runs the except. So in this code, it's going to come in, it's going to try this. This is going to blow up. But instead of giving a traceback, it's going to say, oh, I've got an available except. I'm going to run this except code, and then I'm going to continue on. And so that prints out first -1. So because we set this variable Eister to -1, like a little flag telling us that something went wrong. And then we keep on going, and now we have put in 1, 2, 3, the digits 123, the digits 1, 2, 3, and now it's going to work, but we still have it in a try block, and then this one works, it does not blow up, and then it ignores the except block. So the except block is only triggered when something goes wrong in the code. It is ignored if something doesn't go wrong. So it's like you bought an insurance policy on this line of code, and when things go wrong, your except block springs into action and does whatever it is that you want it to do in the case of an error. Okay, so that's a pretty useful thing. You got to be a little bit careful that you don't overuse it, because if you put more than one line inside the try part and one of the lines blows up, it doesn't come back to the try block. And so in this one here, we have kind of a simple, silly one where we set the string. We're worried about some stuff. Well, the print statement's never going to blow up, so it's a bad idea to put it in try except anyways. Then we do this conversion, and that's the dangerous part. And in this one, it's going to blow up. And so then it's going to go to the except block and then run the except block and then continue. What it doesn't do is somehow go back and finish this. So these lines are gone. So if you look at it like this works. The try starts. Hello. This blows up. It goes to the except. It runs the except, and it continues on. Never runs that code. So it's not like you took out an insurance on the whole block. Any of those lines can blow up in the block, but whichever line blows up, that is the last line that's executing in that block. Okay? So you tend to want, in this particular example, you would probably, the print statement would go out there, and this print statement would come down here, and you would only put in your try block the single line of code that you think might blow up, because you kind of know print statements aren't going to blow up. So this is an example that's a more common real-world example where the user is going to type some data. And it's users that get us in trouble. So our program starts by asking the user to enter a number, and we know that this could be dangerous. So we're going to do it. We're going to put the conversion from string to integer in a try block, and we're going to set -1 if that's a failure. And then if it's greater than 0, we'll say nice work, and if it's less than 0, well, not a number. So first time we run this program, out comes enter a number. We type in 42, which is a string. That 42 goes back into roster, runs in here. This runs, it's fine. That becomes a 42 number, so we skip the except block, and ival is greater than 0. We print out nice work, and we skip the else. Okay, so it says nice work. On the other hand, if we run it again, this time, the input says enter a number, and we're silly, we enter the word 42, but in words, 40, F-O-U-R-T-Y. So that's a string, and that goes into raw stir. And then the execution continues. We run in here, and now this is going to blow up. That's going to blow up. Normally, we would see a traceback right there. There'd be a traceback, but we're not going to because we put this calculation in a try and accept block. It's going to immediately run the accept block, set ival to -1, continue on with the program. See, you are not blown up at this point. And if ival is greater than 0, well, it's -1, so we're going to hit the else clause and print out not a number. So we've done error detection. The user set something that caused a line of our code to kind of blow up, but we put that line in a try and accept block, and so we caught it. And so we dealt with that fact. So in summary, in this, we talked about if statements, we talked about else, we talked about try and accept, how important indentation is to mark blocks where they begin and the end, and an else if and try accept. So up next, we're going to talk about loops and iteration.